So let's just start out with some data. In this case, we're tracking some outcome, achievement, or executive function, or something like that, for a child across middle childhood, starting at age 5, 6, 7, 8, 9, so annual observations. And we've got, let's assume that we've got an outcome that's vertically scaled so that we're not re-norming things every year. And it makes that you can really compare in a cardinal kind of way a 10 to a 4 or 7. So these are, it's a very small data set, but it's one that you commonly encounter in education research. In longitudinal data, this is often the kind of data that you'll have for one child, and you'll have the same data for 1,000 children. We'll be talking about ways of analyzing those data. But let's just see what kind of relationship there is between this outcome Y and age. So it helps to have an average, which in this case is obviously going to be 7. Over here, it's going to be 15, 30 divided by 5 is 6. All right, so this is X bar and this is Y bar. And let me just plot the data, which is the best thing to do if we're interested in getting an idea of what a best fitting line might look like. We've got age down here. And we've got the outcome scale here, 2, 4, 6, 8, 10, 12. And if we just plot the data, we'll plot for age 5 a value of 4. For age 6, a value of 7. For age 7, a value of 4 again. For age 8, a value of 5. And for age 9, all the way up to a value of 10. All right, so if we want to know the relationship between X and Y, one subset question is what's the best fitting linear relationship between X and Y? So if we are constrained to fitting a line to these points, what line best fits those data? And you can think about what best fitting might look like. I need a line. Turns out in a classroom down the hall, there's a pitching wedge, which serves as a nice line. And you can think about, various kinds of lines that you might fit to these points. And as you kind of do it by eye, you end up kind of wanting to balance points above the line with points below the line, right? If you want a best fitting line. And in this case, it might be something like this. Let me just draw that in. All right, can you see that line?
It's really faint.
Thumbs up, faint? I didn't hear it well.
It's very faint. Thumbs down.
Okay. I bought brand new markers for this class. Okay, or you can just imagine what the best fitting line is. So the idea of kind of balancing points above and below the line is the intuition really behind what a linear regression model does. In effect, to think about it, is taking all possible lines, and for each line, each possible line, you can look at the vertical distance and ask, how well did that line predict the observed y at age 5? It underpredicted a little bit, but not by very much. Age 6, the underprediction is a little bit more substantial. Age 7, it's overpredicting, right? We're predicting with the line up here, the observations down here. So you can do this kind of exercise where you calculate the vertical distance. And, you know, intuitively, what you'd want to do is probably just find a line that minimized the sum of all these distances, right? Best fitting means kind of the smallest sum of these deviations. And that's almost what OLS does, but what it in fact does is fit to a criterion of squared deviations. So if you take each of these distances and square it, this distance squared, this distance squared, this distance squared, this distance squared, for all possible lines, you want to end up with the smallest sum of those squared distances, right? And that's all a regression line does. It fits to a line to the smallest sum of squared distances, like the squared residuals, as they're called. And it turns out squaring has a lot of very nice properties. So that's the kind of criterion. We're fitting a line, so the line is going to have a formula of y equals some constant plus some slope times x. And you actually do this calculation, you end up with an equation where a equals -1 and b equals +1. So the equation is y equals -1 plus 1 times x. All right, so should we pay any attention to the constant? Any hands or any unmuted mics? What's the meaning of the constant? What's -1 here?
It's the slope of the line. I'm sorry.
I'm sorry.
Go ahead.
Okay.
No, go ahead, go ahead.
I realized I was going to make a mistake and call it the slope, and really the b is the slope, but it is the y-intercept, and I'm stealing your answer. It's where the x value is 0 and where the point of the y is.
Okay, and Cassandra, is that what you were going to say too?
Yeah.
Okay, so if we want to know what a is, the constant, we just find the value of y where x equals 0, the projected value of y where x equals 0. But the way we've got this thing scaled, x equals 0, this might be 4, 3, 2, 1, 0. So we're down here, and this point is -1. Didn't quite get it right, but you see what the idea is here. So what meaning is there to a -1 score at age 0 in this sample? Anybody?
It's meant to imply like a baseline for our outcome.
Right, but what? But is it a meaningful baseline in this case?
So at age,
Oh,
Achievement at age.
oh, sorry.
This
Sorry,
is at
Renee, you wanna-
birth what your achievement is.
Yeah, it's the intercept is a
So-
meaningless outcome. Sorry, Vere, you want to go?
The intercept is what? So I didn't hear that, sorry.
Sorry, was that for me or for Berenice?
I don't know, Bernice, were you talking?
I was
It's hard for me to
talking,
keep track.
everyone started talking, it's fine. I was just gonna say that at age 0, I mean, it wouldn't really mean anything because that's at birth and the outcome, whatever, the child hasn't really had any experience to really base off of anything.
Okay, so when people run a regression, they often report what the constant is, right? But as a matter of fact, the constant term rarely is meaningful. So we're going to concentrate all of our attention on the slope. So B is +1. That's our estimate of the slope. What is that? What's a common sense interpretation of
Are
a
you
+1 slope here? I'm
Um,
sorry?
We can interpret the slope as a change in y in whatever 1 unit change in x is.
Okay, exactly. The slope is the change in y associated with a 1 unit change in x. So that's always important to keep in mind. And this was the second assignment homework question that I asked, to interpret that 0.14 regression result in the article about poverty and completed schooling. And most of you got it. The 1 unit change, you have to look to see what a 1 unit change was. But it turns out that income was scaled in tens of thousands of dollars, right? So that $10,000 1 unit change was associated with 0.14 increase in completed years of schooling. All right, so this is always going to be true about the interpretation of a slope. And this 1 unit change is something that we're going to talk about a lot because a lot of times you get a coefficient, it might be a standardized coefficient, and you don't know whether it's big or small, and it's always good to kind of take it down to the elemental unit, the elemental question of what is a 1 unit change in x, and what is the change in y? Is that a large change or a small change? So for the education example, it was a 0.14 year increase. In that case, it's pretty straightforward, but in a lot of cases with a regression, you're dealing with a dependent variable. It might be a test score, it hasn't been standardized, and you don't know what a 12-point change is. So it's very important to be able to translate changes in your x variable and changes in your y variable into something that's readily interpretable. Okay, so let's move on then, unless there are any questions so far. This is fairly elementary stuff.
Can I ask a somewhat related question, Greg, about the homework?
Sure.
I forgot to ask this earlier. You said homework is graded, or the syllabus states that homework is graded based off of the quality of the assignments. I'm not quite sure what that means. So for example, on the second homework question, it asks to interpret the coefficient, and then in parentheses, there's a standard error. So did we also need to tell you what the standard error is and how to interpret it and what we can use it for, things like that?
Well, most of you noted that the standard error was a relatively small fraction of the coefficient. Therefore, the coefficient was statistically significant, and that was fine. The main thing I wanted you to concentrate on was what the numerator was all about, right? The 0.14,
Okay.
and to interpret that. Okay, so the second question, or I guess the first question, was to give me a formula for calculating beta, B. And what I had in mind was, I didn't ask very clearly, if you have data like this, what formula do you use to plug it in, into to get the slope, right? And some of you talked about various ways of transforming standard deviations and so forth. But I wanted to get back to just the basics. And if you look at Gordon, if you look at Wooldridge, and if you look at Paul Ellison, right? We've got the basic formula for a slope is going to be the sum as the cases go from 1 to however many cases there are of xi minus x bar times yi minus y bar. That's the numerator. And the denominator also goes from 1 to n, and the denominator is xi minus x bar squared. So in this case, I is just indexing the cases. The first case, if we have I here, this is 1, 2, 3, 4, 5. If instead of having 5 observations, we have 2,000 observations, I would run up to 2,000. So it's just indexing all the observations. And then you've got this kind of weird xi, x bar, yi, y bar, and so forth. I must say, I memorized this almost exactly 50 years ago. And 48 years ago, I forgot. Because it was never useful. I just would get my computer program and plug in data and get a regression coefficient. And then I started teaching, and I realized that there is substantial value in spending a little time with the formula. So let's do that in the context of these actual data. So let's start with the denominator. And first of all, to make things a little bit easier, we're going to, all these x's are subtracted from mean x. So let's just come up with a a, a conversion of the x's so that they're all expressed as deviation from the mean value of x. So in this case, if we have x in deviation form, 5 becomes 5 minus 7 or minus 2. 6 becomes minus 1, 0, 1, and 2. Okay, so those will be the x's that we'll be dealing with. It's helpful to kind of clear away some of the confusing parts of this formula. We'll just center everything around the mean of the x. That's all we're doing here. Everything else is the same. It's a 1 unit change with every progression as we go from observation 1 to observation 2 and so forth. So everybody okay? Denominator. Doesn't involve y at all, right? It only involves x. So we could have these y values be wildly up and down from where they actually are, and it wouldn't affect the denominator at all. And in this case, it's just going to be, we're going to start with the first case, I equals 1. Xi minus x bar is minus 2, right? So it's going to be minus 2 squared. And then I is going to go from 1 to 2, and minus 1 plus a minus 1 squared, right? Then x3 minus x bar, that's going to be 0 plus 0 squared plus x4 minus x bar is just 1 squared plus 2 squared. It's just 4 plus 1 plus 0 plus 1 plus 4, or 10. That's what the value of the denominator is. So it's just a constant. As I say, it doesn't depend on y. The numerator obviously depends on y. But in fact, what it does is help scale the numerator so that you end up with this 1 unit change expression. It's not obvious from the formula if that's the case, but we'll talk a bit more about that soon. So the denominator is just 10. And what about the numerator? The numerator, let's use red here, is going to be, for the first case, xi minus x bar is going to be minus 2, right? Times yi minus y bar. So we've got minus 2 times, what's yi minus y bar? So
Negative.
Sorry to interrupt.
okay.
Right, there are a couple of students that are having a hard time seeing the board. Is it possible now to try and push the camera towards the board? Or we can try during break if right now is a bad time.
No, I've got it right here. Is that better?
I think so, but I'll ask the others who had trouble answer.
Is it that my writing's too small or is it fuzzy?
I think it's a function of like the screen size people have and then proximity of the camera to the board. and then a little bit with the fuzziness.
Okay, and how bad is it?
Looks like Caroline can see it, but maybe it's a good time to pause
Yeah.
and ask if others can see it or cannot see it.
Sure, Caroline, can you see? Can you see it now? Okay,
Yes.
okay. Yeah, so let me know, once I get going, I tend to write small, which is bad. As I say, I'm going to try to get this iPad camera fixed up. It provides a clearer picture and doesn't lose focus. But I don't think it's going to happen today. But next week, we'll have everything all set up. So I asked what, in the case of the first observation, yi minus y bar is. Yi is 4, mean of 6, so it's going to be -2, right? Plus, now we've got xi minus y, x bar is -1, and yi minus y bar is 7 minus 6 is +1. Plus, what's xi minus x bar in the third observation?
0.
0 times 4 minus 6 is -2, plus y minus y bar is 1 times 5 minus 6 is -1, plus I've got a weight of 2 that we're attaching to 10 minus 6 is 4. So we've got +2 times 4. All right, so I promised this would be instructive, so let me try to explain why I think it is instructive. So ignore the y values for a moment and just look at how a calculation of the slope is weighting the different y values, right? Here we've got a weight of -2, a weight of -1, a weight of 0, a weight of +1, and a weight of +2. So if you think about what counts in terms of figuring prominently into the calculation of B, the observations at the end, the first observation, the fifth observation, count twice as much as observations 2 and 4. And the middle observation doesn't count at all. We've got a 0 weight attached to that. All right, so you could have a wild value of x, and it wouldn't make any difference for the calculation of the slope because you're giving a weight of 0. And by the same token, if you've got a wild observation out at 1 or 5, you're going to be giving it twice the weight as if that observation were at 2 or 4. Right? So the further away you go from the mean value of x, the more weight the y value gets in this calculation of the slope. Everybody see that? So some people have argued if all you want to do is get a good slope estimate for a child, let's say, you shouldn't even bother with an age 7 observation, right? Whatever you get as a value for y isn't going to determine anything about the slope because it's going to get a weight of 0. On the other hand, you got to put a lot of money in the first observation here and a lot of money in getting a high quality final observation. And indeed, you could argue, why not just take 2 data collections, one at age 5 and one at age 9. They're going to be so influential anyway in calculating the slope. So the further away you are from the mean value on the x-axis, the more influence you have for a given y value. And if you actually figure this out, you end up with 4 minus 1 is 3 plus 0 is 0. Minus 1 is 2 plus 8, right, is 10. That's the plus 1 regression coefficient. So this formula ends up being instructive because it points out what's important and what's not important in a regression, at least in the regression calculation of B. Okay, so let me put you to work in breakout groups for just a few minutes. Suppose instead of 4, you had a value of 12. And the question is, how would that change the estimates of A and B? Okay, so instead of Instead of 4, we're replacing a value way up here. How is that going to change this equation? Qualitatively, you don't have to come up with an actual quantitative result. So Paul is going to put you in breakout rooms, 5 minutes. Everyone have an idea of what the assignment is? How would an extreme observation associated with age 7 change the estimates of both A and B? Bye-bye. See you in 5 minutes. Right? You're not going to be able to explain as much. But it's true, nothing's going to happen to the denominator because we change y values and the denominator is only a function of x values. And we've substituted 12 for 4. So 12 is a deviation from the average, it's going to be 6. So the formula, instead of having -2 here, is going to have +6, right? Weighted by 0. What's 0 times 6? 0, thank you. So is anything going to change with regard to slope? Not from the formula. And as I was trying to explain to group 4, think about this. You've got really the data are right here. Right in the center of the data, you've all of a sudden got an extreme y value. So is that going to be pulling the slope up to make this closer to that extreme value? Is it going to be pulling the bottom up to make it closer? It's right in the middle, right? So it's not going to have any effect at all on the slope. And you can see that with this 0 coefficient here, anything that you plug in here is still going to end up being 0. So you're not going to have any change. But you can also see it just intuitively. If we're talking about the exact center of the data along the x-axis, it's not going to be changing the slope at all. It's going to be pulling up the line, the best fitting line, because now we're going to have this deviation of the new point from the old line. It's going to be huge, so that can't be the best fitting line. So the best fitting line has to be closer now to that more extreme value, but the slope isn't going to change at all. All right, so if the line's higher, the constant is going to be even more negative. Right, if you think about the projection of this line down to the age 0 point. But the key point, because who cares about the constant, is that the slope isn't changing at all. So we're going to be focusing all of our attention on slopes and on what affects slopes. And in this case, outliers in the very middle of the data aren't going to have any effect or much effect, depending on whether they're a little bit off center, on the slope estimate that we get. In contrast, if you put this outlier, let's say it's way down here at the extreme, or way up here at the extreme of x, right? Can we get rid of this? Let's get rid of this for the time being. We're going to have now this huge deviation from the predicted line that our regression is going to try to cope with. And the best fitting line isn't going to be one that allows for such a big distance, especially after squaring it, but rather it's going to be rotating down for smaller slope. And you can see that in the formula itself. Any sort of deviation that you have in the y value from y bar is going to get this double weight, right? So it obviously is going to affect the formula. And anything down here that's getting a double weight is going to affect the formula too. All right. So, bottom line is that a regression equation is fitting the best line, and it's fitting that in a way that's going to be quite sensitive to outliers, observations toward the end of your ends of your x variable. But the other thing to take from this is that the slope, forget about the denominator for a moment. It's really just, in this case, kind of a weighted average of these points to the right of the midpoint of the x value minus these points over here, right? You're getting minus weights over here and plus weights over here. So, it's really just looking at change in some sense. It's looking at where these observations tend to be in terms of y values, and seeing whether they're lower or higher. In this case, they're higher than these values over here. So there's nothing mysterious about this formula. It's really just giving a kind of a weighted average where the further out you go from the midpoint of the x variable, the more weight you're giving to the y value observations. But at the end of the day, it's just this stuff minus this stuff scaled so that it represents a per unit change. That's all. That's all it amounts to. So every time you're plugging some data into Stata to get a regression equation fit, you're going to get a constant, which who cares? But you're going to get this slope, and the slope is just going to be cranking through this kind of formula using your data. But in the end of the day, It's just this stuff minus this stuff scaled by the unit changes in X.
Hey, Greg. There's now a flurry of questions that
Okay.
I can't manage.
So I was going to take a break. Should we do this after the break? The
I
flurry
think
of questions? Or?
Yeah.
Okay. Okay, why don't we start up again? So there were some chat questions that I wanted to respond to. Tiffany asked, what if it's not exactly in the middle? What if it's a little bit away from the middle? The extreme observation is 4 becoming 12. And you can kind of see what's going to happen here. If it's exactly in the middle, right, we've got a weight of 0. If it's a little bit away from the middle, then the weight's going to be something like 0.1, 0.2, or minus 0.1, minus 0.2. It's going to start to influence the slope calculation, but it's going to have very, very small influence until you move well away from the middle of the data. All right, so it's just a matter of the 0 is true only at exactly the middle of the x-axis value, but it's approximately true if you're close to that, and then it gets less and less true as you move out.
Can I ask
Is
a follow-up?
that clear? Sure.
So what I'm slightly confused about is, so I understand that if the data is if that y point is in the middle and you're affected by that x weight, which happens to be 0, then obviously that slope in the middle is not affected because you have a standardized, you have an x in deviation form of 0. But what if you don't have anything for your x in deviation form, that column of 0? Because those values were x minus x bar, which is 0. So you're saying that's the middle, right? But the middle numbers don't necessarily perfectly match with the mean of the data. They can be the median of the data. So if you have data that is highly skewed, then the mean and the median of your data don't necessarily line up. So conceptually, I don't understand, like, why would it necessarily have to be 0 in deviation form? Like, you can get numbers that would be significantly higher than 0, no? Like 1, 2, 3, that would slightly affect the slope of your line.
If you didn't center on 0 in the way that we did.
Correct.
That's what you're saying, right?
Yeah, it
But,
doesn't have to, right?
we just did that for convenience. You could plug in the 5, 6, 7, 8, 9 values to this formula, but you're always subtracting whatever the mean is, right? And for us, the mean was 0. That was a convenient kind of transformation. But the mean could have been 7, and we would have subtracted 5 minus 7 and still gotten minus 2, right? 6 minus 7 and still gotten minus 1, and so forth. So this formula centers everything on the mean value of x and y. So you can start out with not something where the actual mean value is 0, and you're still going to get exactly the same thing.
So within any real data sets, can you always expect to have a value of x minus x bar be 0? Is that always expected to be true? Because I'd expect there to be at least. Right, okay.
Yeah, so I'm just trying to illustrate some general principles here, right? And, you know, an actual data set, I remember way back when I was taking statistics, I had a, 600 case data set, and I went through and plotted every point in a bivariate kind of relationship. And you'll do this with in the labs. You just end up with this gigantic cloud of points, and it doesn't look like there's any relationship whatsoever, right? And you run the regression, and it turns out there's a significant relationship, but it's really hard to tell. You'll have data all over the place, x values and y values typically, right? So the point I was trying to convey is that in calculating the slope observations that are close to the middle of the X values carry very, very little weight in determining the slope, right? And the further away you get from the middle of the X distribution, the more weight that you're attaching to it. That's universally true for this example and for any sort of data set you're going to be working with. So, don't get too hung up on this exactly zero, close to zero. Focus instead on the much bigger point that relative influence on the determination of the slope is going to be much stronger for observations that are toward the ends of your X values relative to something that's at the middle. And if you just, think about this kind of line balancing exercise that we had, something like this is going to really pull that slope down a lot. Something in the middle is going to be shifting things around the height of the line up and down, but it's not really going to have any effect on the slope. If it's a little bit away from the mean and it's a high value, it's going to pull things up a little bit, but relative to something that's way out here at the end of the X axis or way down there at the beginning of the X axis, something that's a minor deviation from the mean isn't going to have much of an effect at all.
Okay, I'm good. Thank you.
Okay, and the other point was a good one. Won't Y bar change if we stick in a value like 12 instead of 4? And the answer to that is yes, it will. And the question is whether the slope will change accordingly. And I will formulate a clean version of that for next week's assignment question. And you can calculate this yourself. What are people's guesses? How many people? Oh yeah, so you can vote yes or no. How many people think if you plug in 12 instead of 4 that the slope is going to change? Give me a yes or a no vote on your so I can see on the participant list.
To
I'm
clarify,
going to hold you to this.
instead of where's this 12 going?
So the question was, if in the middle of the data we're changing this from 4 to 12, because 12 is so much bigger than 4, we're also changing Y bar, right? So if we're changing Y bar, we're changing the calculation for the slope. It's a different mean that we're taking deviations from. And the question is, are you expecting with a 12 plugged in there and a higher Y bar that this numerator is going to change? Obviously, the denominator is going to change, right? That's not a function of Y at all. But is this numerator going to change in a way that's going to make the slope bigger or smaller? Lauren, was this your yes or no vote? Or is this
Actually, I have a totally different question that goes in a different direction, but so maybe I should wait.
Okay, let me just, yeah, let me just get a little vote here. Are people chatting their responses?
Yeah, I'm not sure if people know what you mean by the yes or no vote, but maybe clarify.
Okay, so it's just a function. Is it a reaction?
No, it's at the bottom of the participants window where you can raise your hand, say yes, say no, go faster, go slower. I think that's what you mean, right?
Yeah.
People are answering in the chat box, though.
Yeah, yeah.
All right.
Ah, weird. And I don't know why that option is
All right.
not available.
Another thing to troubleshoot for next week's class. Okay, we'll see. I'll have you do the calculation as part of next week's 2-question assignment.
Can I ask a burning question?
Yes.
Okay,
Sure.
wanted to ask it before the break, so it just keeps going in my mind. So you started out the lesson saying the units of X are significant, and I didn't really understand that until you broke this down, and now I see how X is so influential. So from this, are we able to determine that if you change the units of X, you can resolve this problem so the middle variables are hold more weight, or is this going to happen regardless of the units of X?
This is eternal to whatever X scaling that you do. But if you think, if you think about it, again, how can anything in the middle of, these can be any values here, right? If you get some linear scale, 1,000, 2,000, 3,000, 4,000, 5,000, you're just, to pivot this line, to change the slope, is going to require, think about it as like a teeter-totter, right?
Yeah, it
If you're
pivots
right in the middle-
regardless.
Yeah, exactly. So you can crank it through, but I hope that you can also see this intuition about what happens to a best fitting line if it gets pulled up by some big middle value, and why. There's just as much reason to think that the slope is going to pivot this way or this way if something is right in the middle. And in fact, there's no reason to think it's going to pivot either way because it's right in the middle. That's kind of the bottom line.
So why then are units?
Does look like that answered your question. What's that?
It does. I guess I wonder then why are units of X significant, and why do experiments change their units of X?
Oh, sorry, that's a totally different point. Because the interpretation of a slope is a change in Y associated with a 1-unit change in X, it's very important to know what a 1-unit change amounts to. Okay, so if this were decades of life, first 10 years, second 10 years, third 10 years, so we're expanding the scale by a factor of 10, and a 1-unit change was a 10-year aging, right? It's very important to know whether this change is associated with just 1 year of aging or 10 years of aging. So in that sense, the scaling of X matters a lot. It's all about interpretation. The scaling of X doesn't matter for the slope of the line that we're estimating.
Got it. Thank you.